Welcome to Ready to Derive. In this video, we're going to explore the Fundamental Theorem of Calculus, Part 2. You do not have to be familiar with the FTC, as it's typically abbreviated Part 1, to be able to follow along with this. This is also known as the Evaluation Theorem, and what it will allow us to do is to be able to calculate the value of a definite integral. And what does a definite integral, say of f of x from a to b, represent? It represents the area under the curve f of x from x equals a to b. So visually, it would be the area of the shaded region. So as you can imagine, if we can learn how to evaluate those definite integrals, it will be a pretty powerful tool. The only other thing you have to be familiar with is the concept of an antiderivative. If that term is not familiar to you, you can check out my video on antidifferentiation. And so you need to know that, for example, the antiderivative of x squared is 1/3 x cubed, and the antiderivative of cosine x is sine x, among other sort of more straightforward functions. No composite functions at this point. So the Fundamental Theorem of Calculus is a fundamentally, pardon the pun, beautiful theorem, a powerful theorem that allows us to work out a complicated area that would otherwise be impossible to find just using calculus. So without further ado, let's get started. So let's begin with an example that illustrates the fundamental theorem of calculus in a very intuitive way. So we're going to find the area under the line 5 plus 2x between x equals a and x equals b, as illustrated with the green shaded region. Now we indicate this, now we know from previous video that this integral from a to b of 5 plus 2x with respect to x actually represents that area. It's the mathematical notation for that area. And what we're going to do, though, is we're going to work it out geometrically, because we have a trapezoid, and the green figure is a trapezoid, and this is the formula for the area of a trapezoid. Now, you have to be careful here, because B1 and B2 are the parallel bases. So B1 and B2 are those sides. They don't look like bases right now because of the orientation, but the distance between the bases is actually referred to as the height. So again, it's this trapezoid is sitting kind of on its height, and the parallel bases are vertical. So now let's think about it. What is the length of B1 and B2? Well, we can find B1, that height B1, by just plugging a into the equation, and that would give us the y value, which would be 5 plus 2a. And similarly, for B2, if we just plug b into the equation of the line, we would get this. So the sum of the bases would be 5 plus 2a plus 5 plus 2b. And the distance between the bases, h, will just be the difference between b and a. So we can tidy this up a little bit, simplify. So 5 plus 5 is 10, plus 2a plus 2b times b minus a. And the half we can distribute into the first parentheses, and we get this. And then if we just FOIL out or distribute out, so we could start by distributing 5 into the parentheses, so we get 5b minus 5a, and then we'll do the same with ab minus a squared, and then finally with b, we get this, and we will see that, oh, these terms at least cancel. So now I want to do something, just kind of reorganize this. So we're going to group expressions with a and those with b in separate parentheses. So we have, let's see, 5 plus 2x, the integral from a to b of 5 plus 2x with respect to x. Because the b terms are positive, I'm going to put them first. I'm going to put 5b plus b squared in this parentheses. And because both of the a terms have negatives, I'm going to factor out that negative, and I'm going to get 5a plus a squared. And in the next slide, we're going to see something very curious. So here's the formula we derived in the previous slide for the area of that green region, an algebraic expression. And I just want to recall that the f of x, that's the equation of the red line, so it's 5 plus 2x. And I want you to recall, I want you to think about, what does this uppercase f of x represent? 5x plus x squared. I'm hoping that you can recognize that that is in fact the antiderivative of 5 plus 2x. So if you take the derivative of x squared, you get 2x, and the derivative of 5x, you get 5, and therefore the reverse process, it would be the antiderivative. Why does that matter? Well, now let's look at this expression up here. 5b plus b squared. Is that not just the antiderivative evaluated at b? And what about 5a plus a squared? Is it not also the antiderivative, but this time evaluated at a? So this leads us to an intuitive understanding of the fundamental theorem of calculus, which is pretty profound. It's that the area under a function, or between the function and the x-axis, over a closed interval ab is equal to the difference in the values of its antiderivative, evaluated at x equals b and x equals a, and then just that difference. So this is pretty amazing. We're going to formalize it in the next slide. So let's just formalize the fundamental theorem of calculus part 2, also known as the evaluation theorem and abbreviated FTC for short. So if f is continuous on the closed interval ab, and uppercase F is an antiderivative of f, i.e. f prime x equals little f of x, then this is true, that the integral from a to b of f of x dx is just going to be equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. And why is this useful? Because once again, it gives us a way to calculate the area under any curve as long as we can find that function or that curve's antiderivative. Now, this theorem can be formulated slightly differently, and sometime in this next form it's referred to as the evaluation theorem. So instead of using little f and uppercase F, we could also recognize that f of x is an antiderivative of f prime x. I mean, f prime is just the derivative of f, so the reverse must be true. So if we replace f of x with f prime x in the integral sign, so right here, notice that the antiderivative of f prime is just f. We don't even have to use a different letter. And this connection is really also very interesting and intuitive, as we will see in the next slide. So let's have a little look at why the FTC part 2 makes sense. And I'm going to bring up the second rendition of the FTC formula, the evaluation theorem. And instead of f prime, I'm going to use s prime. Instead of x, t. And I've even sort of put numbers in for a and b, 2 and 10. So what exactly, if I worked out this calculation, what exactly would I find? I would find this calculation, if I could carry it out, would give me the area under this curve between 2 and 10. So now I want you to think about s prime. Let's suppose that s prime t is the rate of snowfall at time t. So maybe in, inches per hour, how fast the snow is falling. Well, if that's the case, then s of t, or the antiderivative of that rate, should be the amount of snowfall at time t. And then if we sort of put that together, so what would the area under that curve between 2 and 10, under that rate curve give? Well, as we've seen in the past, that should give the accumulation or the net change of snow between t equals 2 and 10. So doesn't it sort of make sense that the way that you'd find the accumulation is you'd say, well, what's the amount of snow at, let's say, that could be 10 p.m., and subtract out the amount of snow that had already fallen at, say, 2 p.m., and surely that difference would give the amount of accumulation of snow between those two times. So this is a really nice way to sort of make concrete sense of the fundamental theorem of calculus. So let's revisit the problem that we started this video off with. And so recall that we found the answer to this integral by finding, well, we did it with a and b, but this is from 1 to 4. So we could do it geometrically by finding the area of a trapezoid, but now we have something much more efficient. So we have the fundamental theorem of calculus. So I'm going to lead you through a couple of methods, ways to evaluate an integral like this. So the first method is to say, okay, let's recognize, let's call little f of x 5 plus 2x. That's the integrand, right? That's what's in here, the integrand. And we know that we need to, so that's little f. Now we need to find big F. So let's just find the antiderivative of 5 plus 2x, which is 5x plus x squared. And then we need to find f evaluated at the upper limit of 4 and at the lower limit of 1. So this is a systematic, kind of a nice way to go about it. So we know that we could find f of 4. If we plug 4 in to uppercase f of x, we would get, that would come out to 16 plus 20 is 36. And if we plug 1 in to there, we would get 6. And then according to this, we just have to do f of 4 minus f of 1. So we would subtract those, f of 4 minus f of 1, which just comes out to be 36 minus 6, which is 30. So that is apparently the answer to this integral sign. Now, you might wonder, it is possible that when we do antiderivatives, I mean, 5x plus x squared is indeed an antiderivative. So is 5x plus x squared plus any constant, like 10. So what if we had added 10 to each of these? So if we added 10, this would have come to 46. And if we added 10 here, this would have come to 16. I hope you can see that 46 minus 16 would give the same answer of 30. So the constants basically would cancel out, which is why we tend to go for the simplest antiderivative. We don't have to worry about the constant when we're solving problems like this. So the other method is maybe a little more efficient, and it uses a special kind of notation. So the notation we use is, what we do is we find the antiderivative of the function first. So the antiderivative of 5 plus 2x is 5x plus x squared. And then we use this special symbol. It's a vertical line, and we put the lower and upper limits next to it. And what that indicates is we've still got to do something with the expression in here. Think of this as a holding pattern where we actually, we don't want to do too much at once. So let's work out the antiderivative first. So the antiderivative is placed here. And then let's just show that we still need to evaluate it at 1 and 4. And then we dive straight into this. So we know that we have to start with f of 4 minus f of 1. So we'd put 4 and 4 there, 1 and 1 there, and then we would work that out. Again, 36 minus 6 equals 30. So the first method is kind of, in some ways, is good. It's sequential and organized. The second method, as you can see, takes a lot less writing and is a bit more pleasing to look at. So, but you can choose whichever one works for you. Moving forward, though, for simplicity, we'll be sticking with method 2. So we're going to evaluate this integral. It looks pretty straightforward, but it's for illustrative purposes, as you'll see shortly. So here is the FTC part 2 with this sort of holding pattern piece in between, so we can practice using correct notation. So if we do this, the antiderivative of cosine x is sine x, and we don't want to forget to evaluate it at the upper and lower limits. So that's going to be sine pi minus sine 0, which is 0 minus 0. Well, that's interesting. How could the area under a curve just come out to be 0? Let's take a look. So here's a graph of cosine x, and if we think about it, well, we have this area here, which is above the x-axis, and this area here, which is below the x-axis. So the green area we know is positive above the x-axis, but the red area, because it's below the x-axis, it's a negative area, an area associated with a negative sign. So so they obviously cancel each other out by the symmetry of cosine. Well, let's take a little bit about and perhaps break it up. Let's work out the area of the green region with the same method. So Let me just change the color there. So sine x from 0 to pi over 2 is sine of pi over 2 minus sine of 0. And we know that the sine of pi over 2 is 1. So let's see, well, let's look at the area of the red section, which would be from pi over 2 to pi. So once again, sine x, pi over 2 to pi, sine pi minus sine pi over 2. And sine pi is, that will be 0, and sine pi over 2 is 1, but there's a negative there, so that's negative 1. And now it makes perfect sense that if the area of this is 1, the area of the red region is negative 1, you add them together and you get 0. What else is kind of remarkable is that we have, if you think about it, the area, this area here is 1. How the area under a curve like cosine x with radian measurements from 0 to pi over 2, how it could just work out to be 1 unit squared is kind of pretty cool in itself. Seems like it would be a lot more complicated than that, but that is the area of that region. It's like 1 square unit. Practice evaluating slightly more complicated definite integrals using the FTC part 2. So let's dive straight in. So the antiderivative of e to the x is just e to the x, and the antiderivative of minus 2x is minus x squared. And prior to this, I introduced this notation for indicating that we still have to evaluate at the upper and lower limits. Sometimes this, instead of a vertical bar like that, it appears in textbooks as a sort of half a bracket. So I'm going to introduce you to that so that you're familiar with however it might appear. And then we evaluate the antiderivative at the upper limit minus it evaluated at the lower limit. And this becomes e squared minus 4 minus e to the 0 is 1. 0 squared is 0, and that comes out to e squared minus 5. Now let's move on to the other one. This next one, it looks like we have a quotient rule. Don't be fooled, there is no quotient rule for integrals. So the first thing we have to do is break it apart into components that we do know how to find the antiderivative. So we can divide x over x squared to be fair, and then 3 over x squared. X over x squared is 1 over x, and 3 over x squared is just that. And it would be good for a moment here to kind of think about what is the antiderivative of this expression on the side here, just to make it less complicated. So 3, I'm going to leave 1 over x as that, because you need to recognize that the antiderivative of 1 over x is ln, the absolute value of x. But for 3 over x squared, it's better to write it like this. So then we can use the reverse power rule, which says that you take the exponent of -2, you add 1 to it, so it becomes -1. And then you don't forget to compensate for that. You would divide the -3 by -1 to get +3. And you can check it. Just take the derivative of 3x to the -1, and you would indeed get back to -3x to the -2. So then let's use this now. So hold on, just to be consistent. So that equals ln, absolute value of x, plus 3 over x. Since I'm going to plug things in, I might as well put it back, shake off the negative exponent. Now another way, so I showed you this method in problem 1. Sometimes actually the complete brackets are written on either side, and then we are going to evaluate it from 1 to e. So we get ln of e, which is positive, so I don't need the absolute value, minus ln of 1 plus 3 over 1, which equals 1 plus 3 over e in the first parentheses, minus 0 plus 3, which equals 1 plus 3 over e minus 3, 3 over e minus 2 is the final answer. So for our final practice problem, we have a particle moving along the x-axis back and forth, and here's the velocity function, and we're going to find the definite integral of the velocity from 0 to 9 and understand what it means. So the most important thing to realize is velocity is just the derivative of position. So I've indicated that as s of t, so velocity is s prime t. In doing that, then it's not really that hard if conceptually to find the antiderivative of that. I'm just finding the position function. So let's use the reverse power rule. So t to the half, I'm going to add 1 to that, that becomes 3/2. And if you recall, to compensate for that, so that the derivative would work out in reverse, I've got to divide by 3/2. And then the exponent here is 1, so t squared, and again, compensating for that square, I would put the half. When I take the derivative of -half t squared, the 2's cancel out, leaving me with t. So now let's work this out. So the antiderivative of v of t we've just established. So 2 over 3/2 simplifies to 4/3, t to 3/2, and then minus half t squared. And I'm going to use the brackets. Kind of, this is my preferred method, so I don't forget any terms, and we're going from 0 to 9. So that's 4/3, 9 to the 3/2, minus a half 9 squared. And then I'm going to subtract out what would happen if I plug 0 in, which is just going to be 0. And if you work this out, you would get 36 minus 40.5, which works out to -4.5. So what information does that give us? That tells us that over the time interval 0 to 9, the particle traveled 4.5 centimeters to the left. That's because of that negative sign. So does that mean it traveled a distance of 4.5 centimeters to the left? Not likely. And if we take a look at a sketch of the velocity function, we see that in this area, between 0 and 4 seconds, the velocity is positive. So in fact, the particle begins by moving to the right. And then after that, so to 9, as we go from 4 to 9, oops, sorry about that, we see that the velocity is negative. Sorry, some technical difficulties there. And there's a lot more sort of negative area than positive. So therefore, it's not surprising that the final position is going to be to the left. And in this case, 4.5 centimeters. And that brings us to the end of this lesson. I hope you found it helpful. And if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.